Welcome to this other section of mastering neural networks with TensorFlow 2. The task we have here is to use machine learning to say whether a given review for a movie is positive or negative. Here's the IMDb site. IMDb stands for Internet Movie Database. And if you go to this link, https://ai.stanford.edu data sentiment, we shall be able to download that data set. It's actually entitled Large Movie Review Dataset. This is a dataset for binary sentiment classification containing substantially more data than previous benchmark datasets, who provide a set of 25,000 highly polar movie reviews for training and 25,000 for testing. There is additional unlabeled data for use as well. Raw text and already processed bag of words formats are provided. We could see the README file contained in the release for more details. So here we could download this large movie review dataset, and when using this dataset, please cite this. So we're getting this dataset thanks to the work from the authors Mas et al. Of the paper entitled Learning Word Vectors for Sentiment Analysis. And for comments or questions on this dataset, you could contact Andrew Mas. Let's see what this dataset actually looks like. We have the training set and the test set, which we could break up into validation and testing. Right here with the training set, we have positive and negative reviews, while this unsupervised section is made of reviews which haven't yet been classified as positive or negative. So we get into these positive reviews. If we look at this, we have Bromwell High is a cartoon comedy. Most probably the title of this movie is Bromwell High. It ran at the same time as some other programs about school life, such as Teachers. My 35 years in the teaching profession led me to believe that Bromwell High's satire is much closer to reality than its teachers. The scramble to survive financially, the insightful students who can see right through their pathetic teachers' pomp, the prettiness of the whole situation all remind me of the schools I knew and their students. So this is a review coming from someone who is like relating to this movie. When I saw the episode in which a student repeatedly tried to burn down the school, I immediately recalled at high. A classic line by the inspector: "I'm here to sack one of your teachers." Student, welcome. The student replies, "Welcome to Bromwell High. I expect that many adults of my age think that Bromwell High is far-fetched. What a pity that it isn't." So our algorithm has to get such a review and be able to say whether it is a positive review or not. Let's now look at the negative reviews. Take this first one. Story of a man who has unnatural feelings for a pig starts out with an opening scene that is a terrific example of absurd comedy. A formal orchestral audience is turned into an insane, violent mob by the crazy chantings of its singers. Unfortunately, it stays absurd the whole time, with no general narrative, eventually making it just too off-putting. Even those from the era should be turned off. The cryptic dialogue would make Shakespeare seem easy to a third grader. On a technical level, it's better than you might think, with some good cinematography by future great Vilmos Zsigmond. Future stars Sally Kirkland and Frederick Forrest can be seen briefly. So this is a negative review, and our algorithm has to be able to get this kind of review or this kind of input and say whether it's a negative one or not. Now take note that at some point this review sounds like it wasn't positive review. Like at this level we have on a technical level is better than you might think. So if the algorithm has a focus on just this part, we may have to say that this is a positive review. But our algorithm has to be robust and intelligent enough to get all the message, understand this message, and say that this is a negative review. We've downloaded the data set and we've seen exactly what it looks like. Let's go ahead to treat this data. Let's suppose for one of the data points in our data set, we have this input text. The actors in the pilots were well organized by the organizers. It gets better every time I watch it. Notice that we have some HTML tags, we have some special characters, we have some punctuation signs, and we have both uppercase and lowercase letters. Now, in order to classify and say that this input is a positive review or a negative review, we do not necessarily need this tags or maybe these special characters. In some cases, we may need this punctuation, but maybe not in this particular case. Or we may not need to distinguish between uppercase and lowercase letters. So we shall see how to treat this kind of input data before they are being processed by our model. One of the processing steps involve turning all this input into lowercase. So we'll notice this capital T turns to a small t, and if we get this I, it turns into small I, and this other I into a small I. This is simply because whether upper or lowercase, our model wouldn't actually take a different decision if we had a uppercase or lowercase. So in order to restrain our vocabulary of possible words, we just convert everything or all the words into the lowercase, such that we don't have to do with double words in our vocabulary. So if we had a vocabulary which says this the as a different word from this the, that's not very efficient. So that's why we have to convert this first into lowercase, such that this is seen as this and it's also seen as this. So this the and this the actually mean the same now in this new vocabulary. So that's it for the lowercase. And then the next process we could do is to remove the HTML tags. Now in practice, many times we extract text from websites via web scraping, and after doing this extraction, we may be left with textual information that contains actually some HTML tags. In this case, for example, this bold HTML tags actually will make this section, that is this it gets better every time I watch it, with all this. So from this dot to this, we'll turn it into a bold. So it's gonna be bold in the HTML page or on a web page. Now the fact that this is bold isn't very useful in classifying the whole sentence or saying whether this is a positive or negative review. So it's needless including it in our model or including it in our data to be used in training our model. The next is removing special characters and punctuation. Now by special characters, we mean characters like the star and then the hashtag. So having to consider this as a single word for training our model is actually useless, as right in the sentence they have no role to play. So it's important that we take this off before training our model. Talking about the punctuations, sometimes it's necessary for us to maintain them, as in some cases we could better train our models by leaving these punctuations, since they make a great difference when being used in some cases. Like suppose we have a problem where the difference will be made when you're either asking a question or when you're either making an affirmative sentence. So if we have a question sign in that kind of sentence, then it's important for it to be used to train the model, since the presence of that question sign will make the model better learn from that data. In some other cases, these punctuations may not be useful, so we just simply take them off. Now, looking at accented characters, in many languages other than English, say we have French language, Spanish, Italian, we have many characters which are actually accented, like this E right here. This E is pronounced as A. In French, it's the accent aigu. We also have the accent circumflex and then the accent grave. These generally are converted into their original form. That's just the simple E. Although in the language itself, they have different ways of being pronounced. So we generally remove these accented characters. So you can see here, we leave from this E accented into this E. And then we go now to stemming. It's important to note that many words are formed from shorter word stems. Let's take an example of the word organized. Organized is formed from a word stem organ, and organizer too can be formed from the word stem organ. This organizer can also be formed from the word stem organized, that's without the R, and this too organized without the D. So the process of stemming actually is about reducing words into their original word stem form. So a word like organized becomes organ, organizer becomes organ, actors becomes actor. So we don't have this S, it's now singular actor. Now, in the case of actors, this actually works fine, because we could consider that when we have the word actors and say we have the word actors used again in the text, then actors and actor can be considered as one word, and that's actually very interesting, or it makes our work more efficient. But in the case of organized and organ, where these two actually don't mean the same thing, with organizer and organ, where they don't also mean the same thing, then stemming actually leads to some errors. Hence, although stemming originally has the purpose of trying to make our input text more efficient, it leads to this kind of errors, so it's not used in practice. The other method which is really used in practice is the lemmatization. With lemmatization, you'll see that organized and organizer remain intact, and then we have this better, which turns into good. So unlike the stemming, which is kind of a brute way of bringing words to their original forms, with lemmatization, the context and then the meaning of each word is taken into consideration. So if you're doing lemmatization here, where you're considering that the words which have been inputted are, say, adjectives, then this better is going to be converted into good, since good, better, and best should mean the same thing. And then bad, worst, worst should also mean the same thing. But then if we're considering this to be a noun, that's if we're doing lemmatization, considering that the words are nouns, then pilots could be turned into pilot, and then actors into actor. So in general, it's important to note that lemmatization takes into consideration context when shortening the words, or when bringing words into some original form or some stem form, whereas stemming doesn't do that. So we'll see how the actors and the pilots were well organized by the organizer turns into the actors, and the pilots were well organized by the organizer. So we see that's the same thing, and it gets better every time I watch it turns to it gets good every time I watch it, because this good will be considered as better. So instead of having two different words, better and good, in our vocabulary, we just have one word, good, which represents better, best, and any other word which may be having good as its original form. So that said, we've converted this initial sentence into this new sentence. The actors and the pilots were well organized by the organizer. It gets good every time I watch it. Notice how for each word we define a specific color. This is to say that each word is going to be one word or considered as one word in our vocabulary. And from there, we could start by creating a vocabulary which is made of they, while noting the number of times they actually occurs. So they occurs 3 times, actors once, in once, and right up to watch, which occurs once. Then from this, we reorder our vocabulary such that we start with words which occur the most. So we have the, which occurs 3 times, it occurs twice, so it leads from this position to the second position, and then the rest can be ordered, or the rest follow the same order since they all occur once. So this is exactly how we create a vocabulary such that when training our model, all words will be taken from this vocabulary, and if there's any word which is not in our vocabulary, we consider it to be unknown. So from this, we have a word to index dictionary which we could create. On this word to index dictionary, we could have a start token. Now the start is just to say that if we have this input sentence, we're going to add this start to the beginning, and then for end we add it to the end to show that our sentence is ended. And then the pad, which is useful in cases where we have many sentences and that not all sentences in our data set have the same length. So we kind of like pad some shorter sentences to fit our vocabulary, or to fit our maximum sentence length. And then the unknown, in the case where a given word or an inputted word doesn't belong to the set vocabulary. And then from there, we now have the vocabulary itself. So we have, for example, the, it, actors, and so on and so forth. So this the is a foot, the it is a feet, actors, seat, and so on and so forth. So we just basically reposition each of these words right up to watch, which is the 18th in our dictionary, which is linking the words to indices. So we see already how we are leaving from the words now to numbers, which is what our model is used to using to train. So when our model sees, for example, the number 4 and knows this is the word they, if it sees the word 16, or if it sees the number 16 or the index 16, it knows it's dealing with every time. So the model don't work directly with the words. So that's the reason why we need to have this kind of word to index dictionary. And also we could create an index to word dictionary, which is just basically done by swapping this term. So we have 0, which is the index now, which is mapped to start, and then 1 mapped to end, and so on and so forth. So basically that's it. Now from this, after creating this kind of word to index dictionary, and then we have this kind of input, so we have the start, and then the end, the part, the unknown, this UNK is unknown, the it right up to watch. Our model also doesn't generally directly use these indices or these numbers, like say 4, 5, 6, and so on and so forth. It uses the 1 hot notation. And we may have seen the 1 hot notation previously in this course, but let's take a look at it. We have with this start, since its index is 0, we have this 18 or this length 18 vector, because our vocabulary has 18 different of these terms, or 19 since we started from index 0. So we have 19 different positions. This vector is made of 19 different positions, and the 0 position is a 1 that's representing the start, and the rest are zeros. And then for the end, we have the first position, which is a 1, and the rest are zeros. We look at this random value, that's the it. For example, we have the it. If we come here, we have the feet. So we have 0, 1, 2, 3, 4, 5. So on this, we have the 1, and the rest are 0. So this is how we have the 1 hot notation of an input sentence. For example, or the one-hot notation of this input vocabulary. So in case we have this kind of sentence, the actors in the pilots, we should just come and say, okay, this is D. Let's take this one since this has already been converted. So we have this day is represented by this, so we pick this up, and then next actors, we pick this up, next in, we pick this up, next day again, we pick this same one up, next pilots, we pick this up, and so on and so forth. So we are not going to be sending in the words directly into our models or just these numbers, but this one hot vectors. Now let's see exactly how our data is transformed just before getting into our model. So suppose we have this input sentence, the actors in the pilots. So we just have this 4-letter or this 5 words. So we take off this where well organized by the organizer to the end. So we don't consider from this to the end. We're just taking this for demonstration purposes. Now, if we have the actors in the pilots, then the one hot representation will have the start. So we have the one here, this one hot vector stat, which we had seen already. And then we have the, so we have the right here, this is one hot representation, then followed by actors, followed by in, followed again by the. So we repeat this one hot representation of the right here, and then pilots, and then followed by end to say that our sentence is ended. And then we have this pattern. Now let's explain this pattern. The way this pattern works is that if initially we have fixed that each input sentence has a given length, so in this case we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if the length is 11, for example, then once we have this input sentence, which is start, the actors in the pilots, and then in order for us to match up with this input of 11 sentences or 11 words per sentence or per input sentence in our model, we need to pad it such that we meet up with the sequence length. So that's why we have this pattern, and so we pad it 4 times to match up, since here we have 1, 2, 3, 4, 5, 6, 7, and to match up with 11 minus 7 is 4. So that's why we pad 4 times. That said, the dimensions of our input array or input tensor is going to be our shape, batch size, sequence length, vocabulary size. Now let's look at the sequence length. In our case, the sequence length is 11, since we have considered that each input sentence should have a maximum sequence length of 11. And in the case where we have a sentence which is longer, like suppose we consider all this sentence, then we shall cut off some portions. So if we have start, the actors, so this is start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we have the end. Obviously, the rest is going to be cut off, so we shall consider only the first words which make up the sentence. In the case like this, where we had fewer words, we then pad. So that said, we have a sequence length such that each of the sentences come with a fixed sequence length or with a fixed length, so that some sequences or some sentences don't have a longer sequence or input sequence as compared to others. Now, we also have this vocabulary size. That is because here in the one hot notation, the length of this vector is dependent on the vocabulary size. Since our vocabulary size is 19, we have a vector which is made of 19 different values. So we have sequence length and then vocabulary size. And this actually forms already a matrix, a 2-dimensional matrix of dimension, sequence length, vocabulary size. And then since we have different batches, or we wouldn't work with just one sentence every time, we prefer to work with many sentences at once. We've seen this already, working with batch gradient descent instead of just a simple gradient descent, we'll add this dimension to say that we have a batch size. Suppose we have a batch size of 12. For each of this, we have a sequence length of 11 and then a vocabulary size of 19, which is what we're seeing here. Although in practice, we may have larger values for each of this. So basically, this is how we leave from these words, because we can have many of the sentences which will form each of these batches, to this output tensor, which now can be used by our model to permit us say whether an input sentence is a good review or a bad review.